go over one example to feel more comfortable about this. Last time we talked about gravitational vector field. It says let vector field F be defined as 2xy plus z, comma, the second component is x squared, and the third component is x. This is your vector function. Well, it says show that this function f of x, y, z, scalar function, x squared y plus xz is its potential function. So if f is potential function for this vector function, it means that there is a connection between these two functions using the gradient. So we need to show that your vector function f is equal to the gradient of this scalar function f. So let's put a question mark here on the left-hand side, on the right-hand side. On the left-hand side, you just copy down your vector function. This is defined as, okay, 2xy plus z, x squared, and x. On the right-hand side, we have to form the gradient of this function. Remember that the gradient of this function is taking the partial derivative of f with respect to x. We get 2xy plus z, comma. Take the partial derivative of f with respect to y, which gives you x squared, and take the derivative, partial derivative of f with respect to z, which is equal to x. Now you need to check to see if these two vector functions are equal to each other or not. Well, it's not very hard to see. The first component is 2xy plus z. The first component is 2xy plus z. So we're happy about the first components. The second component is x squared. The second component is x squared. So, well, they are equal to each other. And the last component for both of them are equal to x. So, we verified that these two are equal to each other. What's the meaning of that? It means that this scalar function is actually the potential function for this vector field. So we say that this vector field is conservative. Since this vector field has a potential function, we say that vector field F is conservative. So let's take a look at this theorem. This is a good theorem that gives us some relief, some assurance about a conservative vector field. Theorem. First of all, suppose you have a vector field. Let f of x and y be a vector field defined this way. P of x and y, I plus q of x and y, j. So this vector field has two components. This theorem says if you have a conservative vector field, if f is a conservative vector field, and if partial derivatives of p and q exist and they are continuous, and partial derivatives of P and Q exist, and they are continuous, then you must have this equality. Partial derivative of P with respect to Y must be equal to partial derivative of Q with respect to X. So partial derivative of P with respect to, I'm going to use a different color, so know that I'm taking the partial derivative of P with respect to Y must be equal to partial derivative of Q with respect to X. So what's the meaning of that? It means that if the equality is not true, then you can say that F is not a conservative vector field. In other words, if partial derivative of P with respect to Y is not equal to partial derivative of Q with respect to X, then for sure you can say that, hey, this vector function, a vector field, is not conservative on the given domain. Then F is not conservative on the given domain. So now I expect you to ask, okay, professor, you say that if F is conservative, the meaning of this theorem, if F is conservative, then the partial derivative of P with respect to Y is equal to partial derivative of Q with respect to X. I give you one-way theorem. I expect you to ask question. When do we have this? When partial derivative of P with respect to Y equals to partial derivative of Q with respect to X gives me conservativeness of function F. What conditions do we need? So if you take the partial derivatives and they're equal to each other, you can conclude that the vector field is conservative. So we need to have a condition on the domain of the vector field. So let me erase this theorem for you, and I'll write it here. So let vector field F be defined as P of X and Y plus Qx and Y be a vector field. Defined on a simply connected region like D. What do I mean by that? It means that, first of all, you can shrink any simply closed curve into a point in that domain. It means that this region D is half connected and any simple closed curve can be shrinked into into a point in D. That's the meaning of that. Then and let partial derivatives of first order, partial derivatives of P and Q exist and they are continuous. If partial derivative of P with respect to y is equal to partial derivative of Q with respect to x, then for sure you can say that your vector field is conservative. It means that we can find that potential function f that it satisfies the condition. The gradient of f is equal to your vector function f. That's the meaning of that. Let me write down the summary on this part of the board. So what we learned so far, we learned that summary. So if you have a vector function like f, P and Q, and f is conservative, and with the conditions that the partial derivatives exist, and continuous, then we have this equality. Partial derivative of P with respect to y must be equal to partial derivative of Q with respect to x. And if the partial derivative of P with respect to y is not equal to partial derivative of Q with respect to x, then we can say that f is not conservative. We also learned that, so these are the summaries of what we learned so far. We also learned that if f is defined on a simply connected domain like D and partial derivative of P and Q exists and continuous. And you have this condition that partial derivative of P with respect to y is equal to partial derivative of Q with respect to x, then you can say that f is conservative. Let's go over some examples to feel more comfortable about this. I'm going to write down these two examples next to each other. The first example says, hey, you have this vector field, vector function, v, f, x and y, which is defined as x minus y. So you have x minus y, comma, x minus 2. And question says, hey, do you have a conservative field? Is this vector field conservative? And second example for you is, let you have another vector field, which is given as f of x and y equals to 3 plus 2xy, comma, x squared minus 3y squared. And it says, is it conservative? Is this field a conservative field, very well. So you have P, you have Q. Let's find the partial derivatives of P and Q. Partial derivative of P with respect to y and partial derivative of Q with respect to x. What are these? This is P and this is your Q. Partial derivative of P with respect to y, not x, is -1. Partial derivative of Q with respect to x is +1. Are these equal to each other? They are not equal to each other. Since partial derivatives are not equal to each other, your conclusion is that F is not a conservative vector field. So you can write, since partial derivative of P with respect to y is not equal to partial derivative of Q with respect to x, it means that F is not conservative. We have to do the exact same thing for this second example. Find the partial derivative of P with respect to y, find the partial derivative of Q with respect to x. Partial derivative of P with respect to y is 2x. Partial derivative of Q with respect to x is 2x. As you can see, these two are equal to each other. So here you have partial derivatives are equal to each other. F is conservative. It means that F is conservative. It means that we can find a scalar function f such that the gradient of f, scalar function f, is equal to your vector field. Excellent. So since this example satisfies the theorem, we're going to find potential function f for this vector function. Since I need space, I'm going to erase this part, and rewrite this vector function here for you and show you how to find the potential function. There are many ways to find potential functions. I show one of them to you. If you come up with different techniques that give you the exact same potential function, that's absolutely fine. In previous example, we showed that vector field f, which was defined as 3 plus 2x and x squared minus 3y squared, is conservative. It means that we can find a potential function, which is a scalar function, a potential function like f, such that the gradient of this potential function is equal to your vector field. Okay. So how do we find this potential function? This is our goal. To find f. This is your job. So, very well. Let us begin. We know that the gradient of that potential function is equal to this vector field. The gradient of f is equal to vector function f. What's the meaning of that? It means that the gradient of f, which is equal to f of x, f of y, is equal to function f, vector function f, which is given to you. This is your function. 3 plus 2xy, comma, x squared minus 3y squared. Very well. We're going to use each equality because you have two vectors. They are equal to each other. We're going to use each equality between components and try to build our function f. So what's the meaning of that? It means that partial derivative of f with respect to x is equal to 3 plus 2xy, and partial derivative of f with respect to y is x squared minus 3y squared. That's the meaning of that. I just took the first components and set them equal to each other. F of x equals to 3 plus 2xy. The first components are the same. Also the same for second components. F of y is equal to x squared minus 3y squared. Perfect. So I'm going to, for example, start by writing f of x equals to, let us start by writing f of x equals to 3 plus, I'm sorry, here you have 3 plus, yes, 2xy. Okay, perfect. So what do you have? It says partial derivative of f with respect to x is equal to 3 plus 2xy. Here I have partial derivative. The opposite operation is taking the integral. Take the integral. The integral of f of x is equal to the integral of 3 plus 2xy. Okay, perfect. Since I want to get rid of x, I'm going to take the integral with respect to x. What do you have here on this side? It means that f of x and y is equal to the integral of 3 dx is 3x plus the integral of 2xy with respect to x is x squared y plus a constant. Guys, this is very important. What is this constant? Is it just a number or a function in y? This constant here is a function in variable y, like gy. If you have an expression in y and you take the derivative with respect to x, this will just disappear. So you get the first equality, f of x equals to 3 plus 2xy. So what do we have here? We build some part of this potential function. So some part of f is built. We need to use this equation to build on the rest of this function.
Professor?
Yes, go ahead.
I have a quick question. So technically,
Perfect. So here you have f of x and y equals to this definition, whatever it is. And at the same time, you know that if you take the partial derivative of f with respect to y, it must be equal to x squared minus 3y squared. So let us take the partial derivative of this guy here to get f of y, which is equal to, this is going to be 0 plus this is going to be x squared plus g prime of y. So let's write gy. This guy must be equal to x squared minus 3y squared. Okay, perfect. We are setting these two equal to each other. The rest is just algebra, then using calculus. So gy, the derivative of g with respect to y, is equal to minus 3y squared. What is g? Gy is defined as negative y cubed plus a constant like k. Substitute this guy back here to get your function. So f of x and y is equal to 3x plus x squared y minus y cubed plus k. This is your potential function. Okay, perfect. So another example. In this example, you have this vector field. Let your vector field f of x, y, and z. So guys, note that I'm adding another variable here. Be given as y squared, comma 2xy plus e to 3z, comma 3y e to 3z. So this is a vector function, and the question says find potential function. Find potential function f such that if you take the gradient of f, it is equal to your vector function f. Let us start. So first of all, we're looking for a potential function like f that satisfies this equation. This is your goal. Goal is to find f. To find f, we have some information. What information do we have? We have information about our vector field f, and we also know that this function must satisfy this equality. What's the meaning of that? It means that if I take the partial derivative of f with respect to x, take the partial derivative of f with respect to y, take the partial derivative of f with respect to z, it must be equal to your vector field f, which is defined as y squared, 2xy plus e to 3z, and 3y e to 3z. Okay, what's the meaning of that? It means that the first components must be the same. The second components must be the same. And the last components are the same. So let us take a look at this. Let us start by setting these equal to each other. Then taking the integral and so on. So it means that f of x is y squared. F of y is 2xy plus e to 3z. And f of z, partial derivative of f with respect to z, is equal to 3y e to 3z. It doesn't matter which one you start with. You get the exact same function, potential function for f. You can just select any of them. you can start by using f of x equals to y squared. Okay, I'm going to start by taking the integral of f of x with respect to x and setting this guy equals to integral of y squared dx. What is important for you? The constant is important for you. This guy says function f of x, y, z is equal to the integral of y squared with respect to x is y squared x plus a constant. Guys, here you have 3 free variables and we took the derivative with respect to x, which is equal to y squared. If you take the integral, the constant is a function in y and z. This is the important part. This is your constant. Constant is a function in y and z. If you take the derivative with respect to x, this guy doesn't have any x in it. So the derivative is just 0. You didn't do anything. Perfect. So now I'm going to use this function and these two equalities to find g of y and z. Well, you constructed your potential function somehow. You know that one of the terms is y squared x, you don't have the rest of it. We're going to use these two equalities to find g of y and z. Well, the second equation tells me if I take the derivative of potential function with respect to y, it must be equals to 2xy plus e to 3z. So I know my potential function has a form like y squared x plus g of yz. The partial derivative of f with respect to y is equal to, here you have y squared with respect to y is going to be 2xy plus the derivative of g with respect to y. I don't know what that is, but I know the symbol. This is g, y and z. So what does it tell me? It tells me that, let me just move this a little bit here for you. This equality tells me 2xy plus the derivative of g with respect to y is equal to 2xy plus e to 3z. What's the meaning of that? It means that I can cancel out 2xy and 2xy, gy, y and z is equal to e to 3z. It means that if I take the integral gy, yz with respect to y, it is equal to the integral e to 3z dy. It means that g of y and z is equal to the integral of e to 3z with respect to y is y e to 3z plus a function that was in terms of, for example, in this case, if you note that here we are taking the derivative with respect to y, so it means that your constant was a function in terms of z, like h of z. Perfect. Take a look at this. If you look back to a function, it is x squared, y squared, x plus g of yz. G of yz, you found some part of g of yz. If you substitute this guy back in here, your function f of x and y and z can be written as, let me write it here for you, y squared x plus y e to 3z plus h of z. Okay, let's take the derivative one more time with respect to Now z, set them equal to each other and solve for h of z. So the derivative with respect to z, so very well, this is going to be 0 plus the derivative with respect to z, 3y e to 3z plus the derivative of h with respect to z. These two must be equal to each other. As you can see, you can cancel out 3y e to 3z, 3y e to 3z. So h, the derivative of h with respect to z is equal to 0. It means that h of z is just a constant like k. We are going back and forth between these two. Now you found your h of z, which is just a constant like k. This is our potential function.